You know, your body has its own dedicated repair crew, working around the clock to fix damage. Well, in this explainer, we're going to zoom in on one of its key managers, a tiny but super powerful peptide called GHK-cu. Let's find out what it's all about.
Just think about it for a second. The last time you got a paper cut or a scrape. Underneath the surface, there's this incredible, complex signaling process that kicks into gear, basically shouting, "Hey, time to rebuild over here." Turns out, that whole operation is directed by some very specific molecular messengers. And one of those key messengers? Yup, it's GHK-cu. It's a naturally occurring peptide that's been getting a whole lot of attention in biomedical research. And today, we're going to see exactly why.
So this is the molecule itself, GHK-cu. And the very first thing you need to know is that this is not some foreign substance. It's a copper-binding peptide that's already in us. It's in our blood plasma, our saliva, even our urine. It's a fundamental part of our own biology.
You know, a really great way to think about GHK-cu is as a cellular foreman, right? After an injury, it shows up on the scene, clipboard in hand, acting as this biological feedback signal to direct the whole construction crew. It coordinates the repair work, ramps up antioxidant activity to clean up all the debris, and just gets things back on track.
So, what does this cellular foreman actually do on the job site? Well, the research points to some really fascinating potential roles all across the body. Let's dive in.
The first, and honestly the most widely researched area, is its effect on our biggest organ, our skin. This is really where a ton of the initial excitement around GHK-cu got started, especially in dermatology and anti-aging science.
And the research here is pretty compelling. Studies are suggesting that GHK-cu can boost collagen and elastin, the very proteins that give our skin its structure and bounce. It seems to stimulate fibroblasts, which are like the little factories that build all this connective tissue. So, the potential results that researchers are looking at range from better firmness and elasticity to even reducing UV damage and smoothing out fine lines.
But its role in the skin goes way deeper than just appearance. The research also points to this foundational ability to heal wounds and even fight off microbes that might try to get in the way of recovery. A huge finding here is its ability to help form new blood vessels, a process called angiogenesis. This is absolutely critical for getting nutrients and oxygen to a healing site. This might be why studies have shown it can actually speed up wound closure. And on top of all that, its antimicrobial properties could help keep wounds clean, lowering the risk of infection.
But the research doesn't stop at the skin, not by a long shot. Scientists are now exploring GHK-cu's potential impact on an even more complex system, our brain and our nerves.
Okay, so it's really important to note that this is based on animal studies, but the findings are just wow. GHK-cu is naturally found in the brain, but its levels tend to decline as we get older. This research suggests it might help nerves grow, calm down inflammation in the brain, and help neurons survive. And because of that, scientists are exploring its potential protective role in neurodegenerative conditions.
And the potential applications just keep branching out. Animal models are now pointing to two more really fascinating areas, protecting the lungs and maybe even helping with pain management.
This just shows you the sheer breadth of the research, right? On one hand, you've got studies suggesting it could protect lung tissue from fibrosis, that's a type of scarring, that can be a nasty side effect of some chemotherapy drugs. And on the other hand, rodent models are indicating it has pain-relieving effects, which could maybe one day open a door to new non-opioid pain treatments.
Okay, so we've seen all the amazing research, but how does scientists actually work with this stuff? Let's shift gears for a second and look at the practical side, the chemical structure, and how it's actually prepped for laboratory use.
So here it is, the technical blueprint. You can see the specific amino acid sequence, glyhis-lis bound to a copper atom. This is the precise chemical identity that scientists are studying in the lab.
Now, a peptide like this is pretty delicate, so to make it stable for shipping and storage, it goes through a process called lyophilization. You've probably heard of it as freeze-drying. It's a really sophisticated way to remove all the water without damaging the molecule structure.
The process itself is actually pretty simple in concept. First, the peptide is frozen solid. Then it's put under a vacuum, which causes that ice to turn directly into vapor. This process, called sublimation, completely skips the liquid phase. What you're left with is a stable, white powder that's all ready for research.